Okay, here we go again with cars going around corners. This time we are going to have no friction, going around a corner without friction, which seems crazy. How can you go around a corner without having any friction? Right? The last video we described how if you're going to make it around this corner, there's your car, you're going to need something pushing you towards the center of the circle. And if it's not going to be friction, what is it going to be? Well, what we can actually do is we can use a banked corner, and that can actually push us around the circle. So imagine this corner is banked, right? It's hard to show on a two-dimensional surface. So what I can do is I can draw the road banked like this. So there's a banked corner, and I can draw the car on the road at an angle. There's the tires, headlights, right? There's the part of the car, there's the driver, and so forth. So we have a little bit of an angle here. Of course, there's that angle like that. Now what we can use is we can use the fact that part of the normal force is actually going to be pushing towards the center of the circle. So let's draw a couple of forces on here. First of all, we always have gravity, mg, right? And now we can draw normal force acting up like that, Fn, right? If there's no friction, then nothing's going on here. And what the ultimate question is going to be is, what speed will work for a given angle? All right, what does that mean? Well, you can imagine that if you're going too fast, you're going to sort of be pulled to the outside. Remember, that's the fake force, the centrifugal force, pulling you to the outside of the circle. So if you're going too fast, you're going to have a tendency to slide out this way. If you're going too slow, then you're just going to slide down. Oops, too slow. You're going to slide down the bank like this. You can imagine if you just stopped and there were no friction, everything would start sliding down this way. So too fast is this way, too slow is this way. There's kind of a Goldilocks zone in the middle. What speed will work for this angle so I don't need any friction and I can just barely go around the corner, right? Any faster, it'd slide up. Any slower, I'd go down. And this is going to end up being in terms of the angle and g. And somehow we're going to get that. So that's what we're going to get to somewhere down here. We're going to get a formula for speed equals. So we need to break up some vectors into some different directions here. Ordinarily, when we are dealing with these banked problems, we shifted our axes to be like this. We did x and y like that. I actually don't want to do that this time, because if I think about which way is this car accelerating, well, it's not accelerating this way at all, right? It's not accelerating this way at all. I want to keep it steady. The way it's actually accelerating is that way. That's the way the acceleration is going to go, towards the center of the circle. Remember, here's our picture. The car's coming around a corner, making a right turn. So once again, coming towards you, making a right turn. And this acceleration is towards the center of the circle, so it's that way is our acceleration. It's hard to think about, right? But that's got to be it. So what I really want to do is I want to set up my axes in this direction, same as usual, y and x. Okay, so let's draw a free body diagram and draw this, and then we can start to break down some vectors into components. There's my car, only two forces acting on it. We got mg, and we got the normal force going up like that. Let's see, which side should I do it on? Do it like that, Fn. Okay, and since my axes are going this way, x and y, that's great. That's in my coordinate system. That's not. So I need to change this. I need to break this guy down into components that are going in my coordinate system. All right, so what we're going to have here is we're going to have a vertical component of the normal force and a horizontal component of the normal force. All right, remember this whole thing is on an angle. There's my angle right there. So hopefully with a little bit of geometry you can realize that that's the same angle as right there. Yeah, so you do the geometry. I don't know which, it's alternate right angle something theorem. I don't know what that means. But what that means is I can write across here on the top, I can write this is Fn sine theta, and this is Fn cosine theta. So the amount of the normal force going straight up is Fn cosine theta. The amount of the normal force going in is Fn sine theta. That's going to be the key part right there, the sine theta part. This guy is responsible for pushing the car towards the center of the circle. These forces are actually going to cancel out. So I'm going to do x direction, y direction, and you'll see something's going to be just a little different than the normal banked problems when you have a box sliding down a ramp, for example. Let's come down here and let's do our y direction first. So in the y direction, what forces do I have? Well, I have mg going down, and I have Fn cosine theta going up. So let's see here. I'm going to pick up as positive. So I get Fn cosine theta equals mg. So that's one equation that I have. Those are going to have to balance each other out because I'm not going to have any acceleration in this direction. Those balance each other out. All right? And then in my x direction, what do I have? Well, I just have one force right there. It's just the friction force. That's it. Sorry, it's just the normal force. That's it right there. No friction, just the normal force. So in the x direction, I just have Fn sine theta. And that's going to equal ma. Because this is a circular motion problem, mv squared over r. All right. What am I trying to find again? Oh yeah, I'm trying to find the speed. So somehow I got to get v by itself. And this is all looking good. You might say, oh, just solve it, but Fn isn't a given, right? So Fn I got to get out of this somehow. So let's rewrite this guy over here. Let's say this guy is Fn equals mg over cosine theta. Don't get confused by this. If you look back at your notes for problems that were just a box sliding down a ramp, it's gonna look opposite of this. It's gonna be mg cosine theta equals Fn. It's gonna be different. So don't get confused. This is a totally different problem. All right. Now I'm just gonna plug this in there, and what do I get? I get mg over cosine theta times sine theta equals m v squared over r. Of course, our m's are going to cancel. Goodbye, goodbye. And then if you rearrange this a little bit, what you're going to get is v squared equals r times g times the tangent of the angle, or v equals the square root of rg tangent of the angle. That's really nice. It's really elegant. And if you want to pick a number here and stick a number in for theta, and then you can figure out what speed will you be able to go around the corner. Too fast, you're going to slide up the hill. Too slow, you're going to slide down the hill. But if you're going exactly this speed, you can actually make it around a corner without friction. So icy road, totally no friction between your tires and the road. If the corner's banked at the right angle, you can make it around the corner. I mean, memorize this equation, and next time you're on a really icy road, if you can go quickly measure the angle of the banked corner, you'll know exactly how fast you need to go around that corner in order for it to work. Yeah. It's interesting to note that the mass canceled out of here as well. So once again, I just want to once again point out up here what's really going on. The normal force, here let's look at this diagram. The normal force, part of the normal force is pushing towards the center of the circle. It's pushing that way. That's what's responsible for making the car go around the corner. This piece of the normal force, Fn sine theta, is responsible for making the car go around the corner. Right? In the next video, we're going to see a banked road with friction, and that'll add in some new elements.